Okay, we're going to start this week's ROCKE-3D seminar, and we're delighted to have Roger Buck talk to us about a recent Nature Geosciences paper that he published related to large igneous provinces, which we're big fans of here. So, Roger, please take it away.
Okay, and so I've jammed a lot into this talk, so I want to give you the punchline first, because Linda told me that there might be a few people who don't know everything about large igneous provinces. So I'm going to do some basics on large igneous provinces, and then get into some data that was new like 5 years ago, 4 or 5 years ago, dating basalts in two of these large igneous provinces, the Columbia River Basalt, which is the youngest large igneous province. It's about 16 million years old. And then one of the fairly big ones, Deccan, that covers about a quarter to a third of India. That's about 66 million years old. And the data in both of these places seems to indicate that a warming trend started several 100,000 years before the onset of massive flood basalt volcanism, before the magma got to the surface. And I've been working with a student who's first author on this paper. His name is Xiaoxuan Qian. At the time, thinking about mechanics of magma extrusion and intrusion. And we had been particularly focused on, I'll talk to you about some particular details that I won't go into in great detail about the Columbia River basalt. But when we heard about this data, we got very excited because it was in line with some thinking that we had. And I'll just, okay, broad brush, tell you that little thinking. We're taking the very simple approach that the density structure of the crust controls when magma can extrude. Basically, how deep, if a magma chamber is at a certain depth, if the density of the pile above it is lower than the density of the magma won't get pushed out. And the simple idea, and I'll show a few pictures about that. But let me get into some of the background. So large igneous provinces, LIPs, there are a lot of them, and I'll mention a bunch of them. But we, at least here, are right in the middle of it, and even Jim Head is right in the middle of it. The Central Atlantic Magmatic Province is one of the biggest, and I'll show you a map of that area in a couple of slides. But the Palisades Sill is just one little tiny bit of that magma. And I should mention a couple of times, and I'll start now, that the volumes of magma involved in large igneous provinces, even just at the surface, are typically measured in the millions of cubic kilometers. So there's a lot of magma coming out. That's why people are interested in the CO2 and SO2 and other kinds of volatiles that may come out of them. I was originally very interested in them because there's a correlation not only between LIP dates and climate excursions, extinction events, but also the breakup of plates. And that's what I first got interested in. So I'm going to tell you probably more than you needed to know about breakup of plates. So it's a little bit of a detour for 20 minutes in the middle of the talk. But anyway, just moving forward. This is a little slow. Let's see, is that moving? There we go. So just to get at the main punch of this, many people are interested in why there's a correlation between extinction events and large igneous provinces. And so this is from a fairly recent annual review paper. And it shows that since the end Permian, there have been at least 3 or 4 major events that have correlated. So what's being plotted here on the axis on the left is the extinction rate, and then age on the lower axis. And you'll notice that these extinction events really define geologic boundaries. And the biggest extinction event was the Permo-Triassic, the one that is exactly correlated with the Siberian extrusive event, the Siberian Traps. It's a very big large igneous province. And then our very own Camp province is the next big one and is precisely associated with the Triassic-Jurassic boundary at 201, 200 million years. And then there's a bit of a problem. The Jurassic Cretaceous is a big event that doesn't correlate in a very clear way. It's always an outlier. And then the most recent big event, of course, is what I always call the KT or the KPG now. The big event that wiped out the dinosaurs. That is precisely at the time of the Deccan, the extrusives that come out of the Deccan Traps. So this is what we're interested in. And of course, there's the Chicxulub impact confusing everything, making everyone argue about, was it really just volcanic gases that somehow wiped out the dinosaurs, which perhaps was happening with Siberia and with the Camp province, or was it impactor related? And I'm going to talk more about the volcanic side of things and not about impactors at all, but I'm not going to resolve this question, of course. But again, just focusing on the general features of large igneous provinces. So this is a nice map from Brian et al. Showing more or less the locations of some large igneous provinces, mainly on land here. I'll show you one later that shows a few more in the oceans. There's always a lot of scientific and artistic license in making these kind of coloring in these things, red and maybe silicic ones of them in yellow, because if you use seismic data, and I'll at least mention the fact that we have seismic data indicating that they sort of, if you look up at the Camp province, the sort of east coast of the United States, they've actually used seismic data to color their coloring to their opinions about where they're going to put things. And they didn't in the South Atlantic. So different people color things in differently as to whether they have seismic evidence for massive amounts of either extrusives or intrusives that are now not at the surface. But on the right is just one view of the aerial extent of the Camp province. So you can see that there are basalts, and the red lines here that you can probably barely make out, and they're labeled red. So the Camp lava flows are meant to be red, but also the very bright red are meant to be dikes, the ones with little slashes. And they're all over the place. And they kind of radiate out from sort of Georgia, southern Georgia or something. And that's a common feature of large igneous provinces, that are big dike events, and they seem to radiate. So I'll mention a little bit more about radiating dikes. But North America and South America was very firmly attached to Africa. And then Africa started to move away exactly when this event happened. All right, and then I said we're going to focus particularly on Deccan Traps that cover about a quarter of India, and they're 66 sort of million years old, and there's some fantastic data that I'll go through on them. And then Columbia River is a fairly small, it looks like a big area if you look at the lower left, a goodly portion of western Washington and well down into Oregon and all along the Columbia River. And the plateau that it goes through is termed a plateau, the Columbia River Plateau. Although I show you some pictures that say we like to call it, in the larger view, take a more planetary view, it's actually the Columbia River Punch Bowl. It's actually a low-lying area compared to the surroundings. But if you're down on the river, it's a flat top plateau with a bunch of tiers of flows. So the flows that you can see in the picture at the bottom, the terraces, they are individual flows, and then they're showing some individual flows over for the Deccan. And the typical thicknesses of the entire pile in large igneous provinces are on the order of several kilometers. So that's typically what you're seeing. Maximum at Deccan is a couple of kilometers. Ethiopia up to 3 kilometers. And then another feature of large igneous provinces is that they often have a trail that we think is a hotspot trail. So here's the Columbia River Basalt Group, CRBG. That is the youngest large igneous province. And it has a path that doesn't go right back to it, but definitely is associated with it, that defines the Snake River Plain, and the little numbers on the map at the right around those little sort of pink lozenges are the ages of the volcanics along the Columbia River. And Yellowstone is the active area now. So it's the continental And this is just a shaded relief image. If you can get yourself oriented a little bit, it's focused on the basin range. The lower left is the Great Valley of California. The coast of Oregon and Washington goes up into Canada. Now, the low area, the sort of punch bowl area, that is the Columbia River Basalt. That's up in the upper left inland. And then the Snake River Plain is the flat place that kind of curls down from it. And if you could see my finger, the end of it, the sort of eastern side. So we're looking, this is sort of east is to the right, north is to up, is Yellowstone. But the Columbia River actually sits about 700 meters lower than the surroundings. And that's what we were working on when we found out about this new data. But let me just keep on with the general features of LIPs. So actually I just pulled up I'm sure there's better things than this, but I pulled up a Wikipedia site and it gives way too much information on this. But let me highlight the volumes. So it mentions some of the different provinces along here. Some in the oceans, like the Agulhas Plateau, the Deccan Traps. There are older traps in India, the Raj Mahal. But let me just focus about volume here. So I'm just circling the volume area. And again, these are very subjective. I mean, I think you have to do real geology to go out and try to estimate the amounts on land. And I think there's a lot eroded away in a lot of places. So down at the bottom, the Central Atlantic Magmatic Province that I've circled, 2 to 3 million cubic kilometers at the surface. That's including Brazil, but there's a huge amount more below the surface. I'll get back to that. Offshore, Antan Java, which is not visible on this map. Antan Java is now run into the edge of Papua New Guinea, essentially, or the Solomon Islands, Solomon Trench. That's the biggest volume that you can see at the surface. Is estimated pretty accurately at around 10 million cubic kilometers. The North Atlantic province that goes into Britain, so the Isle of Skye and the dikes all over the north of Britain and all over Greenland is 6 or 7 million cubic kilometers. So these things are big, but and so there's a lot of material. The mass of basalt would be in the petatons of basalt, even for 1 million, even if it's just 1 million cubic kilometers. And therefore, you're looking at pretty large masses of possible amounts of volatiles coming out of these. And I'm not going to go into great detail since I don't know that much about the constraints on the timing of LIPs, except to say that the timing indicates they're fairly short-lived, that the flows typically come out in less than 1 million years, and dating is getting better and better. And I'll show you some details of dating of a couple of the LIPs. But a lot of people worry about whether there are continuous fluxes or pulses every 100,000 years, 1,000 years. And I can't speak to that, but of course, when you're talking about fluxes, that could be very important to think about the effect on the atmosphere. But then I wanted to mention that probably 5 to 15 times, or one in the literature, one sees estimates of 5 to 15 times more magmatic input below the surface than what we can see at the surface. And this includes just intrusive regions that are just high velocity. So the little cross section is just a schematic idea of a magmatic margin, and almost all continental margins look to be magmatic or volcanic. And magmatic is the high velocity zone is thought to be mafic intrusives that may be up to 20 or 30 kilometers thick in some places. And this SDR is a term that most people don't know. It's a seaward dipping reflector. And these were first seen in the South Atlantic about 1980, and they've now been found all along a lot of margins. And they are piles of basalt that can be up to, again, about 20 kilometers thick. And the piles dip towards the ocean. And details are controversial about them, but it's uncontroversial that they are they constitute a huge amount of material, and they are all associated with large igneous provinces. Here's a little close-up, maybe more than you needed to see, about the seismic structure, sort of a colored in. So the layers on top are the later sediments, the post-rift sediments. This is the little inset map shows you one of the places. This is one of the places they were first seen, and we now have fantastic data. This is from a big German effort and industry analysis of a huge amount of data. And you can get an idea, this is depth converted, that you're getting sort of 8 or 10 kilometers of these seaward dipping reflectors. You kind of lose them in at greater depth, but they tend to be tens to 50 or 100 kilometers wide. So just massive amounts of volcanics, all up and down most passive margins. The origin of these is very well tied. If you ever go drive around the eastern fjords of Iceland, you can see exactly what's going on. There was a wonderful paper, one of my favorite papers ever, Bothersson and Walker, George Walker, a famous volcanologist, and you can't miss the slope of in every fjord in the east and even in the west. Everything dips back towards the center of Iceland. It's the same thing. You get a migrating. So very briefly, what they're trying to show with a 1 through 4 time sequence, dikes coming and then flows. But this is 1963. This is 5 years before plate tectonics was generally accepted. They had to assume plate tectonics to get this structure. You get flows, and then you move apart, and you have more flows on top that load them up. That's what we think these things are. But that you didn't really need to know that. Anyway, this is somebody else's, a more recent compilation showing you more of the large igneous processes in the oceans as well as land. So these are pretty common events, but not happening all the time. And some, like Manihiki and Shatsky, were actually just split apart from Antan-Java. Antan-Java was probably right on a ridge, so they're actually one unit. Anyway, and again, this is somebody who's very liberal in their view of margins, but almost every continental margin is actually formed during a large igneous event. And we think the general view is that they're formed with a plume head or a giant plume coming up from deep. So now I've changed scale completely. Down on the bottom is a cross section of the entire, more or less the entire mantle. It's not no scale given exactly. But this goes back to experiments done by Campbell and Griffith back in the 80s, thinking about how a hot boundary layer at the core mantle boundary, or perhaps upper lower mantle, but most people now think core mantle boundary might, if you heat up the mantle, you might get a diapir taking off, and then a trail behind the diapir being the sort of plume trail that we often see after the main event. So Iceland is the plume that's still going from the breakup of the North Atlantic. And like I said, the Snake River Plain is the plume trail for the last 15 or 16 million years until now. And you can seismically see, so here's a cross section down into the upper mantle under Yellowstone. And there's a very clear indication that there is an active plume or a very low velocity region that's thought to be an upwelling plume in that area. And you can even see it. It's the most outstanding feature in the geoid for continental US, at least at a certain range of, I forget the wavelength ranges from this. So this is sort of the general view. There's some kind of big plume head that picks up an area. It can pick up an area and cause extension, but we don't think it picks up areas more than about 1 kilometer. You can estimate how much extensional stress you get out of that. And if you take laboratory estimates of lithospheric strength at certain temperatures, we should not have nearly enough stress to rip continents apart if it's just uplift. You need the magma. And so that's something that I've worked on. And magma does spread itself all along these margins. So here's an indication of the seaward dipping reflectors and on land volcanism at the breakup of the North Atlantic. Same is true. This is not the greatest figure, but all of the breakup events that affected the southern part of Pangaea, Gondwana, happened in association with large igneous events. So one of my favorites, the Karoo-Farrar, so the southern Antarctica, or southern in this, everywhere you look along the Transantarctic Mountains, you see Farrar basalts. And this is actually the longest stretch. They're probably dike connected. So the Karoo is centered in southern Africa, but the Farrar go all the way to actually, this is Tasmania, actually, that then moved away when Australia split off. But this is 7,000 kilometers across. But this is exactly when essentially the breakup of Antarctica from Africa. Piranha and Tendeka happened at 130 million years, and that was the breakup of Africa. And there's a trail, there's a plume trail left behind of that. And then very, very quickly, I'll just show you what's happened with everything in terms of breakup events of the Mesozoic to now. So here's Pangaea, and then bam, essentially the Siberian traps, there's always something different. Siberian traps came in and did not split things. It's the only big event that it's not a splitting event. Can't split us off of Africa, essentially, leaving a good bit of Africa behind. And then Karoo split away, basically India and Antarctica away from Africa. And then Piranha and Tendeka split South America away from Africa. Deccan split off the Seychelles, essentially. Greenland essentially split off from Eurasia with the at about 58 million years, and we're left with Iceland still pumping away up there. Ethiopian traps split essentially Arabia away from Africa. Okay, so I guess I'm jumping a little bit here. I think I just put these together. Okay, now this makes sense. So I want to talk about, so most of the talk, when I get back to it in about 5 or 8 minutes, is going to be about sills. But I'm taking a detour into dikes. I don't know how much you guys are into magmatic structures, but
none. So tell us.
Okay, so I thought I'd keep this thing relatively basic. Very good. So I took a wonderfully simple picture. We usually think of dikes as being vertical, and I'll usually think of them as being vertical. Technically, a dike is just is a sheet-like body of magma. I'm talking about magmatic dikes. You can have dikes of anything, but they're cutting across layering. But in the cases I'm thinking of, rifting and mid-ocean ridges, the dikes are typically vertical. And mechanically, they're actually very simple in a way. There are a lot of complexities to them, but at the simplest level, they're just fluid-filled tension cracks. And so you have an area that's under horizontal tension, and you have some magma in the system that can essentially come in contact with that stressed rock. If it can overcome fairly low values of resistance of strength of the rock, they can split the rock open. And it looks like once you start one of these cracks, essentially they just go if there's any stress allowing it to open. I'm showing a very tiny dike here. There's no scale on that, but dikes can be anywhere. At mid-ocean ridges,
What do you mean by tiny? Is this 5 feet or is this 500 feet?
I think this is probably a dike that's less than a meter wide or even thinner than that. And these are lava flows in a volcano. So I think this is like a 20, 30 meter section or something there at most. There are some bigger dikes, but an amazing amount of places you go to look at dikes, they're about a meter wide. And we think that's related to the fact that once they start to go into stressed areas, they keep going until they run out of stress. And there's some reasons and then they'll freeze up. There's some reasons that a meter might come into controlling when they freeze up, but that's a whole nother story. But they're what basically splits the plate along at mid-ocean ridges, typically. So these sort of white things are meant to be old dikes that are sheeted on. I'm not going to show you pictures of sheeted dikes, but they're all over geologic exposures of mid-ocean ridges. the latter part of the talk's all going to focus on lenses or sills, so horizontal. But let's think vertical just for the next 5 minutes, because I think that's what relates to maybe the size of these areas and why they split continents. Okay, so this is one of my favorite pictures. I was happy to spend a sabbatical year in Iceland, but it wasn't this year, it was some years later. But I worked on this sequence that's up in the north of Iceland that happened in the late 70s. And this is just for scale, you're looking from the closest to you to the furthest away is probably about 40 kilometers, 30 or 40 kilometers. So that fire fountaining event with flows that's so prominent in the center of the figure is on the order of 10 kilometers long. This is pretty much what's happening now down on the Reykjanes Peninsula. This is the north of Iceland. Anyway, the details don't matter, but we've seen events like this happen where there are propagation events that happen over a couple of days until actually it wasn't until a year after this that some colleagues of mine, Paul Anderson and Brenda Spransdottir, had enough seismometers out to get the speed limit of dike propagation. So how fast do you think dikes crack out? Think it's seismic velocities or molasses in winter velocities?
Molasses.
And it turns out it's somewhere between, it's about a walking pace everywhere we see them, but they were only first monitored with seismicity. So the assumption is the cracking at the front gives rise to bigger seismic events than the later opening cracks and events. And
does it have something to do with also the pressure of the magnetic flow coming into them and the porosity of the rock and all this other stuff?
It's the simplest thing you can imagine, even simpler than porosity. So these people working with, the Icelanders working with this, found out also that there were 20 events in this sequence, and all except the first one opened about a meter. So that's the kind of canonical value of width. We know what the viscosity of magma is within an order of magnitude. We know the driving pressure within maybe a factor of 2 is probably related to the topographic slope at some extent. We know the topographic slope in this area. I mean, the biggest uncertainty is whether the magma is 3 times 10 to the 1 or 2 times 10 to the 2 or whatever, something in that range, Pascal seconds. But if you put those numbers together, meter wide pressure gradients that are sort of 10 MPa per kilometer, no, MPa per kilometer, you get a walking pace. So it's the simplest, it's just flow in a slot. So, and anyway, but it turns out in the geologic past, there are several places where we can see radiating dikes. So you worked with Ernst, and I think he was on this. He might have been part of the et al. So
Buchan is one of his collaborators.
Look at the scale. This is 500 kilometers here. This is a 1.3 giga year, 1.3 billion year old area that's nicely exposed, and the dikes are more or less continuous for 5,000 kilometers. So dikes can go a long way, and I think they go pretty straight. I love the Red Sea. It's almost dead straight. It's not quite. It looks like it ran into the oceanic lithosphere of the Mediterranean, and another branch went off to Aden, and then the weakest branch is still trying to get things going through Ethiopia and ran into the Tanzanian Craton. But I think this is the latest real split up event that happened. And I didn't bring in a little messy little thing to just show you why it happens. So like I mentioned, if you think of the continental lithosphere as gelatin has some strength. If you lift it up, it'll be under tension. I've actually lubricated the surface under this. I'll show you some pictures. So it's under a fair bit of tension. It will do nothing until you inject some magma into it, because magma injection, and I'm not going into any details, can allow pretty normal lithosphere to split apart at easily an order of magnitude lower extensional stress levels than required for faulting. So I'm a great believer that most margins faulting is a secondary phenomenon. It's not always true, but if you do, you can get magma to go through and cause splitting. So here's the setup. There's me towering over a little setup of here's a quarter for scale, and here's a little square patch of gelatin, maybe not quite 2 centimeters thick. And the blood red water basically coming in to represent magma. And there's a little injector for pumping up a ball. That's my injector into this. And when you inject fluid into it, it can go through, and then you can get a propagating crack moving along, and you can split. And I wonder if this will show. Yeah, it's probably, let me speed it up. So it's always fun to see something happening. It's a little slow. Anyway, I'm just beginning to pump some magma into this. So this wants to pull apart this way. It's creating a sill to begin with, but it begins to sort of crack, and then you get a propagating dike.
Yeah.
And then Eurasia, well, Africa over here.
That's how the Red Sea parted.
This is how the Red Sea parted. Exactly. Exactly. 30 million years ago.
I thought it was 3,000 years
It's
ago.
still going. It's only 30 million years ago. Okay, so back to the main topic. So that was just sort of fun to say, well, I got into that partly into this. And let's get back to thinking about extinctions. This is more or less the same diagram I showed before, a little different compilation. But again, a number of large events. This is going a little further back in time, and I'm not sure what there is in terms of a correlation with the end of the Ordovician. And so people like Vincent Cordio have pushed very hard. So I think Ren was a co-author on the first picture that I showed like this. They're trying to show age of flood basalts and oceanic plateaus. So what we see of large igneous provinces. So if you can think of the flood basalts or the plateaus being the visible surface part of large igneous provinces, and then ages of mass extinctions. And there's pretty good correlations for a lot of things. Certainly the end Triassic camp and Permian, like we talked about, and Cretaceous with Deccan. It's not, he pushes a little far with this. Okay, and one reason people are so interested in this is that there's a lot of sulfur and a lot of CO2. I was just trying to look at papers, getting more into sulfur right now. So I've mostly my student and I waved hands about CO2, but now we're trying to think about sulfur. But this was a paper trying to explain one thing that I must admit I do not understand, and we've been talking about it a bit here, that different large igneous provinces seem to do different things to the climate and to extinction. So as far as I know, there's no clear extinction, nor is there any clear climate excursion related to the Ethiopian traps at 30 million years. There's not too much related to Piranha and Tendeka, so you split open the entire South Atlantic, but you don't seem to do too much to climate. Whereas Deccan has a big effect on climate and certainly is related to extinctions, and certainly Camp is, and Siberia certainly is, and arguably Columbia River. So Columbia River is the only geologically large event that correlates with the mid-Miocene climate optimum. So people certainly point to it. I don't know if this is really what's happening. This paper just talks about the fact that Piranha and Tendeka seems to be low in sulfur. Maybe it doesn't pack as big a punch as some other places. And this is a very recent paper trying to look at sulfur abundances in active volcanoes. So this is in particular focusing on a 2,000-year-old eruption of Okmok up in Alaska. I just showed it because there are estimates of the erupted volume and the erupted emissions, sulfur emissions seem to make sense. And I guess they worked with some of you guys here and Lorenzo Bolani on trying to do simulations on how much sulfur injection from Okmok might have affected climate at the time. So this is I think the year before Julius Caesar was killed. That's probably why he was killed, but maybe not. Okay, I won't push things that far. Okay. Oh, the other thing I wanted to talk about is that in thinking about anything about intrusion, so the rest of the talk's really more focused on intrusion as opposed to flows that come out as extrusives at the surface. That data is incredibly important in our ideas about how intrusion happens have changed massively in the last few decades. So the standard view for continental and oceanic magma bodies, so the batholith that is now the Sierra Nevada was thought to be crustal scale, thickness and width, same about in the oceans. It was thought that the lower crust, 5 kilometers of the lower crust of the oceans might all be molten to way away from the spreading center. And so it was this kind of a picture of what people call, this is more of a porcupine, but some people called it an infinite onion that would freeze the side and then more material would come in and freeze again and move it off. This is completely out of the window with seismic data. And I'm not showing the side, I'll show you some seismic data later, but this is the view now of spreading centers. So this is sort of vertical scale, 5 or 6 kilometers for crust. And I didn't want to pull you through a lot of hard to look at multi-channel seismic figures, but it turns out in the oceans where you can take a ship and you can drag a line of hydrophones behind the ship for as much as 15 kilometers and put a really good source. It used to be explosives, now it's air guns. You can get a much cleaner seismic reflection picture of the near surface, meaning the top 10 or 20 kilometers, than you can ever do on land. And so our clearest picture, just like we never would have had plate tectonics without the clear, clean view of a fairly simple system of plate spreading centers. Same is sort of true of magmatic systems. This is an area that it's new, it's ongoing, it's active, it's variable along strike, so there are interesting variations to look at. But one thing that's universal is that the zone of pure melt is not 10 kilometers thick, it's more like 10 meters thick. Very thin lenses that then solidify. Everything geodetically looks like below it is a little squishy. The technical term that one colleague of mine who does those kind of geodetic measurements says. I guess compliance is the technical term. But the melt itself is very, very thin. So it's funny, it's completely changed how everybody thinks about magma. So instantly, Sierra batholith, which was 30 kilometers thick, all of a sudden became transcrustal magma plumbing systems with lots of littles. Now, transcrustal because there is evidence that of equilibration. This is getting way beyond what I really know about, but I understand the petrology indicates that different magmas making it to the surface as lavas have equilibrated at different depths. So they think there might have been multiple lenses. I only showed this picture because it's the best picture I know, and better than anything in our paper, showing one thing that's very fundamental to the paper I'm going to get into finally, is that, so this is pressure in GPa. You can think of one GPa as being about 30 kilometers. So here's depth, it's easier to think about it. Essentially, anything above the lower crust, if you're solidifying basalt in a sill, the CO2 can start to exhaust and get out, not SO2. SO2 and H2O can only exhaust very close to the surface. So this is to be central to the rest of my stories. I kind of like their picture. They were talking about how they seem to believe that a lot of the CO2 coming out of the Kant province did come from the mid crust, but I'm not getting.
What year was this paper?
This is pretty new. I'm sorry I didn't put that. I think it's the last couple of years.
Okay.
I'll look it up for you later. Sorry I didn't put that on. Oh, just to show you some seismic data. And this is one thing that got me into this problem. So I'm going to show you an unbelievably simple model. It's always amazing when there's new data on, or even before there's new data, but if there's limited data or there's a hint of something. So we've known for maybe 30 years that the oceanic crust is layered, and the top layer is sediment, which is often very, very thin. But layer 2 is probably a combination of extrusives and then dikes. But 2A, the very top of that layer, is very low seismic velocity and rubbly, and it looks like it's extrusives, okay? And so it was only 10 years before this picture was taken, or this data was put together, we saw these bright reflectors. So this is an axial magma chamber reflector, which is sort of, so this is multi-channel seismic data. These are basically returns with a scale in seconds of seismic energy that's been sent down from the surface, then come back to these hydrophones and then gathered together and figuring out what it's reflecting off of. So these are layers of reflection. So it looks like there's a pretty strong reflection off the base of this, what we think is an extrusive layer, and a very strong reflection off. And I was aware of some of this data. Actually, it turned out there's only one place. These two cross sections didn't exist when I first got interested in this. I said, well, what could possibly give you a bit of extrusion, but not extrusion all over the place? So when we see we're giving reflectors and rifts, we get extrusion everywhere. Looks like in the ocean, you just get a very limited amount of extrusion. If you convert these seconds to thicknesses, you're talking a couple of 100 meters, typically, sometimes a few 100 meters. And I said, what is the simplest possible thing you can think about? And actually, I should have showed you a picture of from a very good paper that actually really led to my paper. So there was a paper by Emily Hooft and Bob Dietrich. So Bob Dietrich was the lead author on the first paper where they imaged one of these lenses. And he got a student in the next few years to look very carefully at the velocity structure. So if you have reflections, you see where things are. To actually get the depths, you need the velocities. You have to do refraction. I don't need to go into details on it, but there was enough refraction data to look at where these reflectors were at different ridges, and there were different depths. And the prime and simplest idea, so if you just had to sit around and say, why would you ever get a sill? Simplest thing you'd say is maybe magma works its way up until the material above it is less dense, and the material below it's a little denser, and you just spread out. If you think of no strength, if you just think of layers floating on top of each other, and you inject an intermediate density fluid into it, it would come up to the level of neutral buoyancy and spread out. And you'd even do this with gelatins and stuff. People love to make these kind of things, like I do. But they could show very convincingly that since we know the seismic structure very well, and we know the conversion from seismic velocity to density pretty well, pretty darn well, it turns out these sills that they were seeing are nowhere near the level of neutral buoyancy. But they noticed another thing, and they coined this term. They were not at the level of neutral buoyancy, they were at the level of eruptibility. And it was the first thing that I mentioned about eruptions, that it's if you estimate the average density of the packet on top of the lens, that density looks like it's about the same as the density of the magma. So if you have a big wide lens, the pressure on the lens is essentially the overburden, just the weight of that on it. And you can imagine you have just enough pressure to push the magma out to the surface. So I thought it was a brilliant analysis, but they didn't talk about how it might be generated. And I just took the next obvious step. I said, okay, if you imagine you just had dikes, and dikes are definitely, solidified basalt is about 8% denser than molten basalt. You could think of it as 10%. So if you just had that, you'd have everything on top much denser. Anytime you cracked open, and you're constantly pulling this apart, you just want to extrude all over the place. But if when you extrude, so we know that the extrusive rock tends to be rubbly, it tends to be fractured, and sometimes vesicular, and its average density is quite a bit lower than the magma. So now you have two things to deal with. And if you can sort of adjust so what I'm trying to show in the A and B is that if you have a shallow magma lens down to Z1 or Z of the lens, that you would come to an equilibrium, meaning that the average would give you just enough pressure to reach the surface. So I'm sort of showing very low density rho extrusive on top of pretty high density rho intrusives, meaning the dikes, whereas rho magma is intermediate. And the pressure, the sort of static pressure in a magma opening to the surface would be just enough to reach the surface. And if you were the other way, if you had too much extrusive, you couldn't reach the surface. Too little extrusive, you would reach the surface. So actually, I did a little physical demo of this and put this out as an idea in 1995, and my co-authors came up to me and said, well, this is really nice, but there's only one data point right now. There's nowhere else. So let's forget it. So we let it sit for the next couple of years, but they said, but I'm working here and I'm working, another person working there. Suzanne was working one place. And in the next year and a half, we had data from quite a few places. And so the prediction of this, you can put in lots of complications. Who cares about complications? But the first order thing is that the deeper the lens, the more extrusives to get to equilibrium. So if you put this deeper, you need a bigger pile of extrusives. And it looks like it sort of takes off. There may be some interesting feedbacks. And there's definitely that trend. So that flew through geology. That's where we put it out. I didn't put the date on. This was 1997. So anyway, that was sort of what we were thinking of when we were working on this problem of intrusion into large Venus
I've been
provinces.
thinking about this for a couple decades. I now see.
Oh yeah,
Yeah.
oh yeah. I'm not the quickest guy off the mark.
Cool.
But I keep going. The tortoise. I'm the tortoise in this. So actually, I'm showing Deccan, but we were actually working. I'll come back to that. We were working on figuring out this punch bowl that I mentioned before. It's like, why in the world would this area be low? And it's the same for the Snake River Plain. And actually, a colleague of ours, I should have shown a picture from one of her things, and her name just went out of my head, but had actually talked about this idea of having a lot of intrusive mafic rocks. So granitic rocks makes up most of the crust. That's my level of thinking about things. Continent, granite, LIPs and oceans, basalt. Basalts are mafic. These are felsic. That's more common. Granitic, basaltic, basalt dense, granite low density. And quite a bit, in the extreme, you could be 2,600 kilograms per cubic meter for granite, 3,000 for basalt. So we're talking 20% on that order, 15%, whatever. And she said, well, maybe that's what's happening with the Snake River Plain, that you're somehow intruding a lot of material. And we then said, well, maybe it's what's happening. And we're starting to play with this idea. And we combined her idea that that's what pulls the surface down with that idea that we published back in 97 about extrusion. We said, well, wait a minute. What if you come into granitic upper crust that has a density of 2,600 and your basaltic magma is 2,800? You're not getting through it. You're in a nasty situation. You've got a lot of stuff pumping into the crust, and it's probably burning its way through the crust and adding to the crust, but it's going to be kind of involved. And we're beginning to think, and it's also pretty clear from the geologic data that this punch bowl was a punch bowl when the extrusion happened. So there's several kilometers of extrusives here. They didn't extrude and then sink down. They were filling this punch bowl and they're pushing it down further. So we were trying to figure out, okay, does it make sense? Can we apply this simple idea? And it was a pretty simple idea of just saying, can we densify the crust? And then once we've densified it, and we were trying to think about that there might be a sort of a history of magmatism, that the flux of magma coming out of the mantle would get high at some point, might shoot up very high. We don't know how quickly. At some point, it has to wane. And so when as it's going up, you can sort of eat your way through the crust and eat through it, melt it, push it to the side. But the key thing is that when you start to wane, you'll start to cool what you heated up. And you might end up with a carapace that's predominantly basalt, that's then dense enough to force the magma out. So that's it. It's a super simple idea. And the data, I should have shown the data for Columbia River, but there's some pretty good seismic data across showing that the lower crust is pretty high velocity. This is showing left and right. The reason I put this in is to compare global average. This is from Christensen and Mooney. I should have put in all the references to this, but threw this together at the last minute. But this compilation on the left is doing kind of what I was mentioning about Hooft and Dietrich doing. So on the top, so the vertical axis is depth through the crust. So there are not too many places. except Tibet and Altiplano, that are deeper than about 40 kilometers through the crust. And then this is seismic P wave velocity, compressional wave velocity, averaged over everywhere on Earth that we have refraction data. And you more or less have a linear increase in velocity. And it's thought to be actually this change, this sort of a change from almost purely granitic and granite sediments to more basaltic or more
It's
mafic.
amazing how continuous it is.
Yeah, it's kind of like the data. You can see those are error bars, so you can put a nice. Yes, it's amazing, but it is kind of amazing that the error bars are centered on. So it's more or less a linear increase, and it's probably averaging a lot of things. But on that same scale, we're showing one area that there's some refraction data. So we don't have infinite data. We only have data in a few places. So our reviewers weren't too happy with our showing this, but it's all that exists, and showing that it looks like the upper crust in one area under the Deccan Traps is very much higher velocity, and converting that to density on the bottom is apparently higher density. The red is meant to be our estimate of mafic magma density, basaltic magma density. So it looks like the crust has, at least, it's not unreasonable to think it's been densified. Of course, we don't know what it was like beforehand. You know, geology doesn't give us a blank slate to ever work with, but it's not unbelievable that it was a more normal area before it got hit with this. And we got interested in, what are the climate effects that people had talked about. So this kind of complicated figure from Ken Miller et al. Down at Rutgers is showing sea level changes, but also focus more on Pacific Dello 18. So as most of you know, this is a proxy for ice and probably for average temperature on Earth with time. So just look at age in millions of years back to 65. There's this big excursion in the mid-Miocene, and it's right about the time of the Columbia River Basalt. So people certainly point to it as a possible cause, even though Columbia River is not a huge, large igneous province. Then this is the data that got us excited. So first from a couple of different authors. So as I understand it, a couple of methods of dating basalts have gotten immensely more accurate and precise. And people claim resolution almost out of the 10,000 year level, certainly to the 100,000 year level. And so the little dots here are ages of, yes, they're, no. These are estimates of temperature from different deep sea cores. So that the whole scatter of dots within an average line through it. So the black line is an estimate of temperature excursions. Sorry, the bottom axis is age in millions of years. So this is older going to younger. Onset of the major volcanism in the Columbia River Basalt Group is roughly 16.75. So here's difference from that onset age. And then this is this estimated, so this is Dello 18 again, and converted to temperature difference. So kind of a 1 degree warning, at least in this data set. I never know how much to believe any of these conversions, but the cool thing is there's a pretty strong signal now that the dating of the basalts, I'm not showing them in this figure, but sort of between here and here is 95% of the volume of what's extruded to make the basalt group. This is where most of them come out. They definitely were not coming out very much 300,000 years before when things started to warm up. So the cool thing is the same thing is seen for Deccan. So now we're going back in time to the Deccan Traps in India, and they start coming out. Again, this is sort of most of what's coming out is between these are two different methods, blue and red to here.
Was this the uranium lead versus argon argon?
Exactly. But this is sort of, again, the main region of the extrusive flows centered on a little bit before 66 million years. But again, the onset of global warming is about 300,000 years before the earliest possible onset of that. Now here, the same sort of Delo 18 in conversion is maybe 2 degrees. I particularly like the big drop that seems to happen in this and kind of complicated. But we were happy with the idea that when we talked to people, and he said, well, what happens with CO2? So like I mentioned from that figure that I showed before, that it appears that CO2 should exsolve out of intrusions down to at least 20 kilometers depth, whereas SO2 won't. So we were in this paper only focused on CO2. And we said, well, if we make a mechanical model with a combined with a thermal model, we know that conceptually, if we have a waxing and waning of the magmatism, we could have a heating and then a cooling. So we could get an offset. We could get essentially all the material being intruded and unable to extrude could be releasing its CO2 that would be exsolving out and working its way out to the surface. And only once we got a pile above where the magma lens was, when in the sort of waning phases, would we get extrusion to happen. And it's also consistent with the idea that most of the magma is intruded at depth, if you try to make these conversions, seismic velocities to densities. So the idea is sort of the same thing as that little 96 paper about densities, but now saying that if you had material, let's say you had upper crustal density and lower crustal density, and a magma lens a little bit down here, you might have just enough pressure to get it a ways, but not out to the surface. But if you kept, as you moved up, you have less and less. You can imagine you've got the average density of what's above you is more upper crustal. You're in worse shape. But if you can move up and down, so that's sort of what we said. If you move up, you're actually in worse shape. The magma can't go anywhere, actually. There, I'm trying to show pressures. So the dark line is meant to be lithostatic pressure through the rock. And this is if you could try to have a crack come out of it, just assuming static pressure, it would not go up. It will only go up when the pressure in the magma is lower than what's the pressure around, or higher than the pressure around it is pushed up. It's pushed up. But we were saying if you could go up, and then as you cool, you intrude gabbro on the top. That's basalt that's intruded at depth. It's called the gabbro. You could end up with now a solid density for the gabbro that's as high density as the lower crust. And if your sill is here, then you have plenty of pressure to get to the surface. You can erupt big time. And the only question was, is a couple of knobs, particularly what do you do for the thermal constraints? What do you do for the fluxes? There's a lot of knobs to twist. The basic idea is straightforward. We can twist a couple of knobs and get 300,000 years. I wouldn't stake my life on that. But here's this is actually more detail on the ages of the basalts. Well, maybe I should have shown this. So the Deccan, these are the two different methods. So I guess the brown is the argon, and the red is the uranium lead. That sees major pulses happening that kind of are cool. And the data is not quite as clear. This is just the average of uranium lead data on the Columbia River basalt. But these are our model. These are the data, and then I'll show the model results. Sorry, I guess I showed that already. So these are the model results that we ran along. Essentially, I'm sorry, it's kind of detailed. I don't want to. I'm about done.
Okay.
So tuned to Deccan and tuned to Columbia River. The green is sort of our model runs that match the data fairly well, essentially by having the fluxes set. So anyway, our interesting question now is what does SO2 do? And the cool thing we're coming to you to ask is how do we start dealing with? We think there's a good case that SO2 doesn't come out until the extrusion. It could be a perfect 1-2 punch. You warm things up for a couple 100,000 years, and you freeze the living daylights out of things. So sorry for going over, but thank you very much.
You're saying that the dip here is the SO2? Is that
Well, that's
hypothesizing?
That's what I hope.
And you
Yes.
didn't put the KT boundary up there, the impactor boundary. Where is it at?
Oh gosh, it's It is, actually, it's at zero
Yeah.
relative to KPG.
Right, you just didn't identify it.
I didn't identify it. Oh, well. There's too much, there was too much physics to talk about, or mechanics, or geology and everything.
So in theory, it could have been at the coolest point when the impactor hit. Oh, interesting.
Yes. So who knows? But I like the idea of a 1-2 punch.
Yeah, yeah. I've heard people discuss this before, this 1-2 punch.
Oh, really?
Yeah, but I think I've heard the reverse, like freeze them and then bake them out when people
Oh.
thought maybe the SO2 came
That's a 2-1.
earlier.
That's a 2-1 punch.
Benjamin Black at Rutgers had a paper that's just like that.
But the opposite, meaning the flip, it's just like that.
Cool.
Yes.
Yeah.
Okay, I'll have to talk to Ben about that.
Yeah.
He probably has more data.
He might.
He's pretty good
He might.
with the data.
Oh, that's really.
We just have an idea, looking for some data. Or inspired, certainly inspired by this data.
So you didn't mention any hydrogen getting up, or you just don't care because it will be water and.
I don't know. I just sort of building off these simple mechanical models, and they're ridiculously simple.
And we don't have good constraints on the amount of CO2 outgassing per se. He's looking at temperature, right? He's looking at the
Yeah.
oxygen abundances. We don't have good constraints on.
Well, I'm asking you because, of course, because I'm interested in the moon more than this
Right.
planet, and it looks like there is a lot of hydrogen outgassing. It quickly escapes, but it stays still a while. Yeah, I mean, in the oxidizing atmosphere is probably not a big deal because it will just, I guess, settle as water. But if you have reducing atmosphere, it will stay and it will give all you also like good heating.
Greenhouse.
Yeah, greenhouse. I guess if you emit it together with SO2, it probably balance it.
Oh, we have a
Oh,
online question from Gavin. Go ahead, Gavin. You have to unmute.
Hi, thanks. I had two questions, one of which you answered already, so I'll skip that one. But I'll ask the second question. So you didn't really mention the PTM, but that's a period that I'm kind of particularly interested in, and the evidence there for intrusions in the North or the nascent North Atlantic seem to suggest, or I think that I understood, I might be wrong, that the intrusions were into sediments, so sediments with a lot of carbon in them, not basalts. So would that impact your estimate of how much carbon dioxide would make it into the system, and possibly even the levels of methane, perhaps?
absolutely. And I think people have pointed to the same sort of thing happening for Siberia. And there is some data that there were some carbonate basins that were intruded by the Siberian basalts. And then certainly people have pointed to exactly what you're saying for the North Atlantic. And I must admit, I'm in a way, fairly new to this literature. I mean, I sort of dove into it when we wrote this paper. Now that I'm thinking more about SO2, I'm diving back in. But I was just looking at a couple of papers, I think Ben Black having done some work on this, and people are trying to differentiate between the organic and the inorganic carbon. So there's a lot of effort. I don't know the status of that. I know one of Ben's papers, and I'm not sure, I don't know the details of it, whether it was I know I saw one camp paper. I'm not sure if his was Siberian, since he's worked a lot on the Siberian traps. But he was making a point in that paper that wherever he was looking, that a significant fraction looked like it was crustal, and as opposed to organic material carbonates that had been reactivated, that it was more deep. And then the paper I showed that pretty picture from of the multiple magma lenses, actually that was the story behind that paper, was deep CO2. They were trying to say that a significant fraction of what that was focused on camp. So anyway, I don't know the status of thinking about the North Atlantic, and it certainly is a good candidate, what you're saying. the variability of basins above large igneous provinces or affected by large is a good way to explain the variability in their response. And I certainly don't know if that's not happening or happening.
Okay, great. Chris, go ahead. Thank you, Gavin.
Yeah, just well, first, just a question about this plot that you have up. I didn't follow the references here, but this black curve, is this like some simple model that where does it come from?
Well, the black curve is the average of this data from of Del 18 from deep sea cores.
Oh, okay. Yeah, I was just saying like having like a 2-degree rise over a couple 100,000 years. I guess it's meaningful. I don't know, would this lead to big extinctions? It's kind of like the modern rise in global warming, but over like 100 times as long or something like that.
So you're saying it's not a big excursion? Is that what you're implying, Chris?
Yeah, I mean it's like comparable to the what we're thinking about to 2100, but not on a much slower time scale. Not that it's unimportant from a climate science standpoint, but I don't know if it would be leading to big extinctions. The other thing I wanted to say about SO2 though is I guess the problem I see with SO2 two things. One is, I mean, there's some literature like common air, like last millennium and Holocene volcanoes, that the thing with SO2 when you get to eruptions like bigger than Pinatubo, much bigger than Pinatubo, the effect sort of saturates because the particles kind of get too big. They become less efficient scatterers, even start to absorb IR, and so like, you just don't get arbitrarily cooling for large amounts of SO2. But then the other thing is just the life. It's such a small lifetime compared to CO2 that I would say the rapid cooling and then warming is a more plausible story. But the rapid cooling would be like a few years. You just don't get. But I guess one way around it would be something else, like black carbon. People talk about that, like nuclear winter. Like if you get something that absorbs and can be self-buoyant in the atmosphere and just stay in the atmosphere for much longer. People talk about that with nuclear winter, but kind of hard to cool by a lot and for a long period of time with that.
Well, I must admit, another problem that people have brought up about all this is that, and you see it in the literature on this, is that it's not clear how basalt flows throw SO2 up into the stratosphere, right? We think of Pinatubo or big explosive eruptions, and it's not clear that these are explosive eruptions. Certainly a lot of the flows don't seem to be. But there is some literature talking about that if you give off enough, you'll get convection that will somehow transport a huge amount of material. Again, it's not stuff.
You need a lot of power to get up to the stratosphere.
It seems like it would be hard.
And these don't seem those kind of volcanoes. They've never been traditionally seen that way. So it's always funny how they always talk about how they produce all the CO2 or SO2 in the upper atmosphere. But how does it get
Well,
there?
you produce a lot of heat, so I guess there is some convection.
But guys, SO2 is a cooler even if it's in the troposphere. It doesn't need to be in the stratosphere. Well, I don't know why you would fixate on that.
Okay.
Well, that's
Then
what
it
people
doesn't
say.
last long at all, not even
Oh,
2
but like,
years.
it hasn't got a long lifetime in the atmosphere. But if you have continuous fluxes for 100,000 years, then you have elevated SO2 for that entire time.
But it rains out pretty quickly in the troposphere.
We have demonstrated over the last 50 years that you can maintain high levels of atmospheric SO2 that cause cooling for decades longer than its residence time. So
good point. As long as you keep it pumping up, yes.
As long as you keep pumping up, but you're talking about an event here that is 100,000 years long. So I don't see that that's a problem for you.
No, you're right. You're right. I mean, it just for some reason in the literature they always talk about SO2 in the stratosphere, but you're right. You don't have to be there for it to cool.
Okay, that's good to know.
Good point.
Okay.
But in the literature,
even if it gets to the stratosphere, though, like you still need that continuous pump because the e-folding time for like Pinatubo, for example, is 2 years. The
residence time is short. Yeah.
Yeah, it's probably when people talk about volcanoes, they mean also the dust which gets to the atmosphere, and dust you have to go get to very high up. So maybe that's why I can
Okay. Any other questions online or here?
Yeah, well, I guess I have a bunch of questions.
Well, not too many. We're a
Yeah.
little over, so.
Yeah, so your CO2 gas, so you're saying it happens basically very deep already. So I wonder, do you think there will be any difference if it's mostly intrusive or mostly extrusive volcanoes? Will you have more CO2 or less CO2?
Yeah, I think, yeah. Well, I don't think, I think I'm told by my petrologic associates that beyond well, shallower than a certain depth, maybe 20 kilometers, the CO2 will get out during solidification. That it won't, that way it'll be supersaturated and get out and exsolve. So I don't think it matters where for the CO2. It's just that it's getting out of the mantle and getting shallow enough to exsolve. I don't think it matters if it makes it to the surface,
but what triggers actually CO2 outgassing? It's just when you reach certain pressure, then it starts basically.
No, just solidify enough. I think it partitions out of the solid, and so if you had a magma that's solidifying again, my very, very low level.
No, I think you say very clearly.
Knowledge
He
of
says
this.
when it crystallizes, the
Oh,
CO2
okay.
comes.
Good. When you don't know the details, it's good that you can put things simply, I think. That's all I understand is that it partitions into the melt, but it's not that soluble in the melt. So it's sort of those two things. If you're solidifying the magma, the more and more CO2 will have to come out at some point, I think.
I'm asking because again, we had like a big discussion about moon that like if you have extrusive volcanoes, then I guess it's kind of obvious that you get CO2 out, but if you have intrusive, then there was an argument, then you don't get much CO2 because it kind of stays in the crust. So you think it will?
I think it would get out, and you're not hitting high pressures anywhere in the moon. I mean, you'd have to be at a couple hundred kilometers down to be comparable.
Yeah, the pressures is below.
Sure.
That's,
1/6.
that's good to know.
Yeah, the gravity is much less.
Gravity is a
low
lot
pressure.
less. Yeah.
But of course, the redox state of the magma is very different on the moon, probably than Earth. I'm sure it's the same, and that might play some role in the chemistry of what comes out.
Yeah, I think
Jim probably can say something about that. Yeah, Jim, you want to say something?
Yeah.
Use video back.
Yeah, no, I think
Jim.
it's that what you say is true, that the situation on the moon is a little different, but I'm also concerned, and Roger and I have had this conversation before about the diffusion from intrusions, exsolution of CO2. You don't see a lot of dikes with a lot of vesicles in them, and even because the magma is coming up at a very rapid rate, and so those are all things that need to be integrated together to be sure that the exsolution of CO2 at kilometers, tens of kilometers, maybe depth, a couple tens of kilometers, is sufficient to actually diffuse, first of all, to crystallize out as bubbles and then diffuse. I'm not sure about that. That's all. And Roger and I have had this conversation, and we'll continue the discussion. But I think this is a really nice theme to think about, because it's pretty powerful and could change a lot of thinking. My petrologic colleagues are a little dubious about the diffusion aspects, or just uncertain, I guess I would say.
Okay.
But like everything else, maybe because nobody's ever thought about it before. So, it's absolutely worth pursuing.
Thanks, Jim.
Thank you.
Jim.
Yeah.
Okay. I think we'll call it quits there.
Well, thank you for coming, and sorry for going over.
No
but
worries. It was very interesting.
appreciate the good questions, and this is the first airing of the SO2 story. So to speak.
Okay, excellent. All right, I'll end the
Bad fun.
Or